Hi guys, can everybody hear me?
Yep.
Great. Today I'd like to introduce to you not one, but three professors that I've had the great pleasure of working with. First, my PI, Dr. Carolina Arias. Carolina received her PhD in microbiology at NYU, studying virus-host interactions. As a postdoc in the Gaiman lab at UCSF, and then at Novartis, she studied the genome-wide transcriptional and translational regulation of KSHB. Prior to joining UCSB in 2016, Carolina worked in the Derisi lab at UCSF, where she used drug screens to identify compounds that could be used to curtail Zika infection. Her current research focuses on understanding virus-host interactions and using these interactions to gain insights into basic cell biology. Next, I'd like to introduce Professor Diego Acosta Alvear. He earned his MS and PhD degrees at NYU studying transcriptional plasticity of the unfolded protein response. As a postdoc in Peter Walter's lab at UCSF, Diego studied the inner workings of the UPR and the wiring of the proteostasis network in health and disease. In 2016, he joined UCSB faculty, where he continues to investigate the molecular mechanisms by which cellular stress response networks either reinstate homeostasis or promote cell death. Last, I'd like to introduce Professor Max Wilson. He received his PhD in molecular biology at Princeton University in 2015 under the supervision of Drs. Zamir Ghiati and Ned Wingreen, where he combined theoretical and experimental techniques to understand the role of mesoscale structures in metabolism and cell death. For his postdoc studies, he stayed at Princeton to work with Dr. Jared Towicher, where he developed cellular optogenetic tools to dissect how information is transmitted from signaling pathways through the central dogma. Max joined the UCSB faculty in 2018, where he continues to develop optogenetic tools and use them to investigate the design principles that enable cellular signaling networks to process information. And without further ado, I'll hand it over to the presenters.
Thank you, Zach, for the introduction. And as you mentioned, today I'm going to tell you a bit of a different story. This is how some of us here at MCDB and BMSE got together to try to think of ideas on how to confront the COVID-19 pandemic in our community here at UCSB. Before that, I think I want to take a moment to acknowledge that these are difficult times that we're living through. And under these circumstances, gathering like these are really important. So thank you, Ethan, Emma, Says, Joel, and everybody who helped organize these and bring us together in something that we love, that is science. And especially the topic of this retreat, which is diversity in STEM. And in the words of Koheli Dutt, acknowledging implicit bias and promoting diversity and inclusion doesn't only enable better science, it's a crucial first step for fixing a broken STEM culture. And I think that all of us being here together really is one of the big first steps in this direction. So thank you for all your work. Before I start with the COVID-19 story, I want to tell you a little bit of what we do in my lab. We started doing research here at UCSB about 3.5 years ago. And in my group, as Zach mentioned, we work on virus-host interactions in cells that are infected with herpesviruses, Zika virus, and coronaviruses. But don't worry, not the one that causes COVID-19, some that we can actually use safely in the lab. I'm not going to tell you much about these. I'm going to speak to the BMSE and MCDB students in November with more details about my work. But we try to answer two main questions. The first one is, how do viruses make proteins? And we want to find out, how are these viruses hijacking the cell components to translate and fold the proteins that they need to make new viral particles? Our goal is to identify crucial factors that we can then modulate with inhibitors to develop them and explore them as possible therapeutics to develop antivirals that are much needed, as we currently know. We have found two factors, one involving translation initiation and protein chaperone, that when we inhibit, we block viral replication. So we're following those two. In the second one, we are exploring a question that I started working on once I moved here to UCSB, and is how do viruses cause disease? And this is a project, or a couple of projects, that we're working together with Dennis Clegg, And we're trying to establish retinal cell culture and retinal organoids as platforms for us to model disease in the retina. Particularly, we want to know how herpes viruses and Zika virus, which cause damaging diseases in the retina and lead to the blindness of children and adults, how are these viruses damaging the cells in there? And what are the responses in this organ that we can probably modulate to help curtail disease? What I'm showing you here is a retinal organoid that has been infected with a fluorescent tagged herpes virus. And you can see that we have very good efficient infection, and we actually know that these organoids make viruses and can infect other cells. So we now have a very good model system that we can use to, again, explore disease. However, as for all of us, March came with the COVID-19 pandemic and we closed shop. But that didn't mean that we stayed still. I remember a conversation that we had with Diego, Ken, and Max on March 14, which was 3 days after the pandemic was declared. And we started thinking, what can we do working together to help our community deal with this pandemic? We all bring expertises that are very different. Diego is a cell molecular biologist, Ken is a neuroscientist and systems biologist, and Max is a molecular and developmental biologist. And I'm a virologist. Sometimes we tend to see science very differently, but so I'm going to show you in very complementary ways. So we decided to see what could we do to confront this pandemic. And as we saw it, we had 3 options. We could work on prevention, on diagnosis, or on treatment. To work on prevention would mean that we have to develop a vaccine. And we know that we need a lot of resources, time, and experience in vaccinology to do this. And we didn't have any of those. So we left that behind. Then we talk about treatment, and some of us in the group, we do have experience developing or assaying compounds for viral infections, so that was something that we started thinking about. Indeed, we had some early conversations with our colleagues at UCSF for the development of aeronaps, which are antibodies that can be aerosolized and bind the spike protein virus and help prevent infection. We did some early experiments with them, but we quickly realized that our expertise was going to be better used here. We had a skeleton crew, and we were spread very thin, and we knew that our friends at UCSF were going to be okay with expertise there. So we stopped that collaboration early on. And that left us with diagnostics. And this is what we explore a little bit further, because we know that testing is essential to control outbreaks. We know that the diagnostics help us understand virus transmission and develop control strategies. And as we saw it, we had 2 options. One was detect viral components in samples, and the second one was detecting antibodies. The first one was going to tell us about active infections, and the second one about exposure. We decided to go with detecting viral components because we wanted to identify individuals in our community that were actively. And to do that, that day, March 14, we just basically pushed the go button and we ordered all the reagents that we needed for us to do here at UCSB the RT-qPCR method for the detection of SARS-CoV-2, the virus that causes COVID-19. This is considered the gold standard and was vetted by the CDC as the method of choice pretty early on. How it works is pretty simple. We collect a swab sample, extract the RNA, which is the material, the genetic material of the virus, reverse transcribe it and do a qPCR. If there is amplification, the polymerase will displace the fluorescent probe and fluorescence will be emitted. If there's no amplification, there's no fluorescence, and that's what you see here. This is how a positive and a negative sample would look like. We started doing some experiments here with in vitro transcribed pieces of the viral genome, and it was very successful. We were able to detect it in samples very easily. It did work as advertised. Probably 2 weeks after we started doing these experiments, we got a call from the public health department and Cottage Hospital, where they were asking for reagents because they were running out of them for testing. And we donated about 600 reactions, which was more than half of what we had in hand, to the public health department so that they could continue the COVID-19 testing. But that brought to light another difficulty with this testing, was that reagents were going to run out very quickly. And we didn't feel that we could take them away from the medical community. So we decided to start developing our own testing, and Max is going to tell you more about that.
Thank you, Carolina. So as Carolina alluded to, no test really has been designed to be scaled to the level that's needed for testing during a pandemic. And so we set out to address this issue by designing like a low cost, and accessible test while also maintaining sensitivity of the gold standard test. So we decided to go with, we decided that the method that would address this and also be orthogonal to current testing infrastructure, so we wouldn't take reagents from those that needed them, would be to be early adopters of a CRISPR-based test. So if we look at any CRISPR-based detection reaction, of which there are many, there are three basic components. The first is the amplification of the nucleic acid that you're testing for. The second is picking a Cas enzyme to do the nucleic acid guided detection or activation of the Cas enzyme. And then the third is actually detecting the activated Cas enzyme. So we decided to go with, next slide, Caroline. We decided to go with, for amplification, thermocycling PCR over isothermal amplification because of how easy it was to obtain Taq polymerase. We decided to go for Cas13 based activation over Cas12 because Cas13 afforded us an extra step of linear amplification, and thus we thought would boost sensitivity of the assay. And then finally, we decided to go for fluorescence detection over lateral flow strips because lateral flow strips were expensive, hard to get, and we thought eventually fluorescence detection could be used in some sort of point of care compatible testing environment where you, for example, used a cell phone to report results. So knowing, you can go back for 1 second, but knowing the pros, we decided to go forward and address the sort of barriers to implementing the tests that we decided to choose going forward. So we were able to deal with the barrier to Cas13, which was simply being able to make enough of it to be able to do large-scale testing. And luckily for us, we had two wonderful postdocs who I want to shout out to, Jennifer Rausch and Eric Valois, who were able to develop a purification protocol for Cas13 that's used by many labs to this day, which is allowed us to purify hundreds of thousands of reactions worth of tests per 1 liter purification. So having that hurdle, remove that hurdle, we really just needed to address the hurdle of cheap hardware in order to scale our test and make it low cost. So luckily, we were able to address both the amplification problem and the detection problem of expensive hardware by embracing the sort of DIY bio movement, where we found very low cost, battery operated thermocyclers and these fluorescent visualizers, which are, at 1 or 2 orders of magnitude cheaper than the current detection equipment that's used in the lab. And they had the plus side that they could actually be run completely off the grid via batteries. So that's when we decided to name our test CREST, which stands for CRISPR-based Rugged Equitable Scalable Test, because this test really can be done anywhere completely off grid, doesn't require any specialized equipment or training. So really, that really left us to try to assess the cost of the reagents. So here you're looking at the cost of on the bottom row, the cost of our test in comparison on the left in comparison to some of the gold standard tests out there. And we found that even without getting sort of negotiated bulk pricing discounts, that CREST was significantly cheaper than all the current tests at the level of purchasing reagents. But also, we were really proud of the fact that we had designed an assay that didn't make any sacrifices at the level of sensitivity. So if you look on the top left panel, you can see that our test CREST can still detect 10 molecules per microliter, which is essentially the limit of detection of most tests. But it's also the cheapest. If you compare that, TaqMan can as well, but of course, it's more expensive, so on. So we wanted to do one final check and make sure that our test, that CREST worked well in the more complex sample environment of a clinical sample, which has things like saliva, mucus, cell debris, and stuff, et cetera. And so here are just two pieces of data where on the y-axis is the signal that comes out of a CREST assay. And then we did side-by-side comparison on the exact same sample of the gold standard RT-qPCR test. And I hope you can appreciate, there's really nice concordance between these two methods. So having developed this test, we really had one more barrier to deploying it at large scale, which was that of sample extraction. And I'll hand the talk over to Diego to tell you how we address that.
Thank you, Max. So yes, as Max mentioned, we came up with this robust, rugged test that could essentially be field deployed, but we were still strapped by the necessity of purified RNA as an input for detection reactions. So we addressed this issue by developing an easy, low-cost method to extract RNA, and not only RNA, it became a method to extract all macromolecules, as I'm going to show you in a minute. We called our method PEARL, which stands for Precipitation Enhanced Analyte Retrieval, and it's a very, very simple method in which we formulated a buffer solution that disrupts cellular membranes and viral envelopes, and subsequently we precipitate all macromolecules in the sample with a carrier with linear acrylamide and isopropanol. So you can recover all the macromolecules in the sample by centrifugation, and it's significantly less expensive than the columns that we use in dedicated RNA extraction kits, which use silica-based columns and cost about $5 per extraction. So our PEARL method costs about 20 cents per reaction, significantly enhances the accessibility of the test. And of course, we made sure that it's equally sensitive as the commercial RNA kits. And what I'm showing you in this scatter plot is a comparison of RT-qPCR reactions done with PEARL extracts or with purified RNA used using dedicated extraction kits. And we tested for the presence of viral sequences, SARS-CoV-2 N1 nucleocapsid sequences, as well as RNase-P, which is an endogenous control that's a host gene. And you can see that the correlation is almost perfect between PEARL and dedicated RNA extraction. So the performance is equal. Now, having said that, we're still, at that point, we were still limited by the need of a tabletop centrifuge to precipitate the material. And we were motivated to go full steam ahead and develop a field deployable test. So we drew motivation from the work of Manu Prakash at Stanford, and we decided to make our own hand-cranked centrifuge. So a student in my lab, Michael Costello, 3D printed this centrifuge that takes 6 tubes, and we can make it spin using fishing line. And you can achieve G forces of close to 4,000 G, and that's enough to precipitate macromolecules for subsequent use. And that made PEARL very versatile too. So here I'm showing you a Western blot with a PEARL extract to detect, in this case, not SARS-CoV-2, but Zika virus in cells infected in culture in our lab, Juan Carolina's lab. And we can detect Zika proteins down to 10,000 cells using this method. Now, we have robust methods that are essentially field deployable and facilitate the access of testing, and we hope that it would lower the barrier of luxury testing around the world. So the last thing we wanted to do is confirm that they have public health utility. So now that we have them, can we deploy them in a meaningful way that would address a public health challenge? And that's a third piece of our story that Carolina is going to tell you about.
Thank you, Diego. So what we decided to do with the methods we developed was surveillance. Basically, the question that we had here was how many people in our community are carrying the virus but do not show symptoms. We know that about 40% of all people infected do not have any symptoms whatsoever, and that presents a very high public health risk. So in order for us to carry out this surveillance project, we've had to form partnerships, and we did so with Dr. Lynn Fitzgibbons at the Santa Barbara Cottage Hospital. She's an infectious disease doctor who is brilliant, and we worked together with her and her team on the medical aspect of this project. We also work very closely with the student health office here in UCSB with doctors Ali, Laura, and nurses Betsy and Holly, who basically helped us set up all the infrastructure that we needed to collect samples. Of course, as we're going to also tell you later, this work could not have been done without the help of our and the dedication of the lab members from the COSIC lab, the Wilson lab, the Arias lab, the Acosta lab, and of course without the support of the Office of Research and Vice Chancellor in Candela. And this was really a team effort. Everybody was working towards the same goal, completely self-illustrated. And I'm going to show you how successful that was. So what we did was recruit 1,800 healthy individuals, asymptomatic, from our community. We know from this group we had 72% of subjects that were students, most of them residing in IB and Goleta. So it's a very good representation of our population here at UCSB. We collected our samples in 2 cohorts. The first one from May 28 to June 11, we collected 732 samples. We had to take a break during summer break because we didn't have people to assay. And then our second cohort was June 23rd to July 2nd, and we did 1,076 samples at that time. The protocol was, again, pretty simple. This is the first time that we evaluated for surveillance. This was the first study that evaluated for surveillance, self-collected oropharyngeal swabs. These are a very powerful method of sample collection because it really reduces the exposure to our healthcare personnel and reduces the need for protection equipment. So it was pretty easy to do, and it was very accessible to everybody. Once we had the swab, so we did was extract the RNA, and we submitted every sample to CREST in order to validate our method as a possible method for surveillance. And we used also qPCR as a gold standard and a comparison for our method. And what we found was shocking. So what I'm showing you here in red is the prevalence in asymptomatic individuals in our 2 cohorts. In gray, we have, in the gray bars, we have the cumulative cases that were diagnosed and reported by public health department in Goleta and IB. What we saw was that in our first cohort, between May 28 and June 11, we detected no cases. There were no samples that were infected. When we came back from the summer break, and I should note here that at this stage we were still in stage 2 of the reopening stages, so we were still under lockdown. Santa Barbara opened somewhere around June 13 to 15, and at this point we had restaurants and bars that were open. 2 weeks after that, when we came back from summer break, the first day that we did testing, we picked up some cases, and the second day we picked up some others, and the third, and so on. In total, we picked up 9 cases. 8 of those were confirmed by clinical diagnostics. What is interesting is that this timing of the upsurge that we were detecting, so we were able to detect the leading edge of an outbreak in our community, and the dotted line shows the projection of the number of how the cases were going to increase with time. Again, what is interesting is that this is 14 days after bars and restaurants were open and we stopped the lockdown. This really shows you that the community interaction can change rapidly the rate of transmission. From the 8 cases that were confirmed, 6 of them followed up with student health and reported symptoms. 2 subjects had classical symptoms, anosmia and tiredness. 2 had mild symptoms that could have been confused with a mild cold, and 2 were completely asymptomatic. None of the participants reported fever as a symptom. We then decided to look at the viral load in the study subjects, and we were able to get some symptomatic samples from the public health department. And we compared the viral load using 2 sites in the viral genome, N1 and N2. And what we saw was that in our asymptomatic cohort, here in red, the viral level, the viral load was very similar. There was no significant difference with those from symptomatic patients here in purple. This was very worrisome because that means that the levels of virus in some of these individuals can be very high, again, representing a high level of transmission or a high risk for transmission. I should also mention at this point that I'm not showing you the data, but when we compared the performance of CREST and the RT-qPCR, it was basically the same. So both of them perform at the same level, just talking about the robustness of our assay. So this showed us that the methods that we developed here were of public health use, that we could use them for our community. And when we look back, we developed a tool that allows us or helped us confront the pandemic here in our community. So where do we go from here? Well, again, one of our goals was to try to offer any help that we could to our community. Besides developing these methods, we have helped establish a COVID-19 lab on campus, and I'm happy to report that we can now do diagnostics for our community here. We also provided the blueprints for a surveillance program at UCSB, and what that means was there was a lot of room for improvement from the first version of our surveillance studies to the ones that are now in place. This is run by one of our wonderful nurses, Nurse Holly Calaveras site. And I'm also happy to report that Pearl is used for all surveillance tests done in the UCSB COVID-19 lab. Today, we have processed about 2,000 samples, saving over $10,000. Thank you. Saving over $10,000. And not only that, but we also saved the use of columns and other RNA extraction kits that can now be used by the medical community, and we can use our own developed methods for surveillance. We're also interested in helping other communities outside of UCSB. For that, we translated CREST into Spanish to be able to help spread these methods in Latin America. We're also talking to our colleagues in Ecuador to make CREST and Pearl accessible to communities in Galapagos Islands, for example, where access to regular testing is pretty difficult. We're also developing what we call the CREST in a backpack. And the idea is to take all the Spartan components that Max and Diego showed you, these little thermocyclers, fluorescence viewers, and our hand centrifuge, and all the reagents that we have processed and developed here to be able to, again, take testing to places where we don't have access. We are also right now working on automating these processes for us to be able to increase our throughput and, again, offer more testing to everybody. And we are also sharing reagents and protocols with other labs. We know that labs in the Netherlands and Israel and Berkeley are using our testing, our Cas13 plasmids and protocols to make the enzyme. So with that, I want to circle back to the beginning. All of this work would not have been possible if we didn't have our wonderful and diverse team. This was really a lot of people coming together from different fields of science and healthcare. We had grad students, postdocs, and PIs working side by side. We had people from different ethnicities, and I think we have more than 6 countries represented in our teams. And all of us came together to work for this. And I think that that was part of the secret for the success of these projects. And all of us keep working together. I can tell you that Max, Ken, Diego, and I are going to continue working on many projects after this. And with that, I want to thank everybody who was part of this project, our wonderful UCSB team, Jenny, Eric, Carlos, Michael, Sabrina, Morgan, Chimay, Francesca, Zach, Ryan, and Naomi, the team at the College Hospital, and our team at Student Health. And thank you all, and we're happy to take some questions.
Thank you for keeping us healthy here in Santa Barbara.
Go get tested.
Yes.
Everybody can go. We can go weekly. So go, take advantage of this.
I have a quick question. Let me throw in a question. So, yeah, what's the in the field? What do you think the minimum time frame for testing and getting a reliable result is going to be?
Oh, so that's a good question, because we hear a lot of things from different places that it takes a week to test, that it takes 10 days to get your answer, and that's not worth it. Our assay can be done, we can have from the moment of collection to the moment of reporting results. It's about anywhere between 6 to 24 hours. So for our surveillance studies, we had the commitment with the public health department and the people in the hospital to produce our results within 24 hours. And so it was really, you know, a heroic effort by our postdocs and students on generating that, but every single result was reported within 24 hours for a study. And now here in our UCSB COVID lab, we can also achieve that kind of 24 to 48 hours. Max?
So, well, in practice, so 6 hours, you can get it down to 6 then?
Yeah, yeah. I think among all of the tests that exist now, there's a trade-off between sensitivity and speed. That's you can be more careful and let amplification steps go longer, right? But you lose that takes longer, obviously. So
where's do you have a sweet spot then that seems to be sort of a good balance of both?
Well, I mean, it's really like a value judgment. How important do you think it is to get like the test to be as sensitive as possible? I mean, I think our test is pretty close. When we have it fully streamlined, we can do this and we can turn the results around in 5 or 6 hours. That's not like you at the level where you would take the test before you, for example, got onto a flight, which people are looking for something that's more at the level of 1 hour. And there are tests. Feng Zhang has a great test called, that can do that, but you lose sensitivity. And we know the Abbott ID now is another example that the White House famously used, which of course is drops a couple of logs in sensitivity, but takes an hour.
Just to add a little bit on what Max just said. So when we were developing our methods, or gold standard was to never lose sensitivity or be at least equally sensitive to qPCR all the time.
Yeah, that wasn't a trade-off we were comfortable making, basically, because we didn't understand, we still really don't understand how infectivity correlates with viral load.
So this is Denise. I have a question for you. I'm not an epidemiologist at all, and so I don't know quite how to think about this, but if I just, on first principles, think about it, I wonder if like testing people weekly is good for just monitoring the asymptomatic, like establishing what's the frequency of asymptomatic, pre-symptomatic people in the population. But if you actually wanted to like squash an outbreak before it happened, like detect one person in Bio 2 who was COVID positive before they got, before everybody else got it. So it seems like you would need to test more often, like every day or something. And I don't know what the current theory is about that, like what, because that could really have a very practical implication for how many people we let in the building, what the density is that we allow, and so on. Because if we could detect a person, right away, then maybe we would let more people in. So I don't. How are you all thinking about that?
Yeah, that's a great question, and I have also to make the disclaimer here that none of us are epidemiologists, but we have tried our best to get educated. There's a lot of discussion on the frequency of testing, of course. So right now there is the debate of, do you want to do regular testing with lower sensitivity, or do you want an assay that is going to be very sensitive and just do it less often? It also depends on the dynamics of your population, right? So, and the stage that you are in, lockdown versus no lockdown, or orange versus red. So I think that this is probably a big answer, but it depends on each community. So yes, of course, if we could afford it, which is the other issue, if we could afford it, we would test everybody every day, right? But it starts adding up when you start, even if we reduce the costs as much as we can and as much as we have, it's still pretty heavy economically.
Yeah. So would it make more sense to test higher risk individuals every day and lower risk people? Let's say if I'm only going in once a week, then maybe I'm a low risk person and you don't need to test me every day, but maybe the people who are higher risk.
Yes, that's a good idea, but we also have to take in consideration the compliance, right? It's like how, do you make it mandatory for certain people and, optional for others? There's a lot of factors that feed into how do you approach your community for testing so that everybody is compliant and also that you protect them. So it's a very good question, but I don't think that there's one solid answer for that.
Mm-hmm.
So there's another little detail there is that if you want to keep the same turnaround and without sacrificing sensitivity, that requires heavy manpower. So we need a lot of personnel to test on a daily basis.
Mm-hmm.
We might have time for one more question.
Yeah, hi. This is Dennis. I typed one in. Great work and great talk. Thank you all. But related to Denise's question, are there plans going forward to test everyone on campus using this assay? And maybe, I know Stu's involved in this heavily, but will this become a major hub on campus for testing everyone?
Yes. Stu's probably in a testing meeting right now. Stu, you're here. Yes, I thought he was running a testing meeting. We're using a lot of different methods. So we have actually selected 3 different platforms that use different reagents, just in case we face shortage of any. So right now what we're doing is we are submitting the documents to have CREST be FDA approved. So we just finished doing a bunch of experiments that they asked for that are pretty lengthy. And so we are in the last process of submitting our EUA or Emergency Use Authorization approval. So once we have that, CREST is just going to give us one more tool in our toolbox to be able to keep the testing going. So it would be, as we see it, it would be one of the platforms that we would use in parallel with others. And also, Max is doing a lot of work in his lab to try to automate it so that we use robots and also we can have more processivity with the samples.
When moving towards the EUA, what we had in mind is to build in redundancies as many as possible to allow frequent testing as Denise asked a minute ago. So the more you have under your sleeve, the easier it gets.